Okay, welcome back from spring break. And I think you can see that we're changing things up here a little bit, having spent a lot of time finding volumes using solids of revolution in a variety of ways. And that topic can be extended, and I think I will go back and do some of that. But coming up on the radar here for some of you is the AP Calculus exam. And as a result of not being in school and remote learning and the state of the pandemic, they're doing things just significantly different. And hopefully, you've been reading your emails from Brad, but there's going to be two questions. You're going to be taking it in the comfort of your own home. It'll be open book, open note. And while the email didn't exactly say, and I poked around and I couldn't exactly find out, it seems clear to me that you'll be able to use your calculator for all the problems. What that says to me is that they're going to be hecka hard, and that we should just be looking at the free response questions. I'm going to just do a series of them and then ask you to attempt them on your own and remind you that it could be a really good idea for you guys to coordinate a meeting where you can collaborate and work within the live board. So don't forget that aspect of things. Okay, so for those of you who are not taking the AP test, this is still super good for you. And I mean, I think it's more important to do this that for reasons of just remembering and rethinking the big calculus picture than it is to try to study for a certain test that, in my mind, isn't a make or break for anybody. Okay, so in the spirit of just reflecting and thinking about differential and integral calculus as we know it so far, these problems are fantastic. Okay, so here I go. People enter a line for an escalator at a rate modeled by the function r. So the first thing that I'm going to continually keep in mind is that this is a rate. Okay, so this is a rate of change scenario. And it's a piecewise defined function, and it's a complicated function. That's why it's actually on the calculator section. That for 0 to 300, for time 0 to 300 seconds, it goes on to say later on. This is the model that represents the rate at which people are entering the line or lining up. And then after time 300, no more people line up. So then it just flattens out after that. Okay, so RT is measured in people per second. T is measured in second. Remember, people per second. So that's another, clue that we're dealing with a rate. It's important to think about that. And then as people get on the escalator, they exit the line. So, they wait to get on the escalator. They get on the escalator. So they're exiting the line, and they're exiting the line at 0.7 people per second. And so that's also a rate. And I guess this constant makes sense because the escalator moves at a constant speed and people are spaced in a consistent manner. Okay, meanwhile, there are 20 people in line at time 0. Okay, so there's a line, there's an escalator, and there's an exit rate that we need to keep our mind on, and that's 0.7 t. And for every second that passes, 0.7 of a person is exiting the line. That's what it says right here. Okay, meanwhile, There's 20 people in line. So there's sort of 20 people hanging out there. And then there is the idea that people are joining this line at a particular rate. So there's a enter rate, and then that enter rate is this R at t function. Okay, so this is not a rate, that's a constant. Okay, so let's tackle the first question. And the first question is, how many people enter the line for the escalator during the time interval from 0 to 300? Okay, so then this is integral calculus. So what you would need to remember at this point is that the integral of rate of change gives total change. So that the integral of the rate of change of t dt from 0 to 300 is going to equal the number of people who join the line. So that's the total number of people entering the line. So that is something that you can type into a calculator. Now, that's a really complicated function to type into a calculator, but we'll get into that in just a minute. So here then is a time to talk about a strategy. I'm not going to go to my calculator exactly yet. I'm going to sort of go to the calculator as I need to. So I might need that number to do, the next part of the problem, but then again, maybe I won't. And I'm sort of going to save all of my calculator strokes until I need them, right? So I'm just going to think this through conceptually and not get bogged down in the computations for as long as possible. Okay, so that's going to be some number, and I don't know what it is, but we'll get to that if we need it. Now then, let me bring over part B. And it looks like I can just fit this in down here. Make it a little bit smaller. Okay, so during the time interval 0 to 300, there are, don't really like how it's now off center. Okay, during the time interval 0 to 300, there are always people in line for the escalator. Okay, how many people are in line at time equals 300? Okay, so the number of people in line at time 300 would be, so let's just go ahead and write this out, the number of people in line equals. All right, that equals the number of people who have joined the line in the first 300 seconds. Okay, we already know what that is. So that's actually what we found up above. Okay, so note to self, I'm going to go get that number and put it here. Draw a little arrow there. But then we're going to need to add to that the 20 people that were already in line. And then we need to subtract from that the number of people who have left the line. And the number of people who have left the line in the first 300 seconds is 0.7 times 300. Okay, so now it seems like a time where I should go ahead and grab my calculator and compute that so I can drop that number in there. I mean, I could have written the integral in here and just done it completely abstractly, but let's not spin our wheels doing that. Okay, so calculator. And all right, so here there is a lesson to take in also. And the lesson is that it's extremely likely as you do these multiple parts, these like free response problems with multiple parts, it's extremely likely that this function is going to be used more than once in some capacity. So it's going to be annoying to type that. It certainly is going to be annoying to type it multiple times. So a little trick that I'm sort of taking on at this point, I've done probably 7 of these, is that I'm going to just write down the function and then copy it and then paste it as needed. Sometimes I'm going to paste it and then take its derivative, and sometimes I'm going to paste it into an integral, like I am on this problem, but it'll avoid having to write it out more than once. Okay, so I'm not doing this integral yet. I'm just getting ready to build a copy. So it's 44 parentheses t divided by 100 cubed. Oh, I'm going to go back here and just make sure all these things show up nicely. Times, just in case there's any weird calculator issues. 1 minus x divided by 300. And then that's to the 7th. Okay, so since I'm going to use it a bunch, double check it. 44 x over 100 cubed 1 minus x over 300 to the 7th. Okay, so sounds good. Now I'm going to copy that. And just in order to make sure I actually have it copied, look in the paste. Yeah, see, I don't even see it in there. So let's get rid of that. Oh, clear that. Are you sure you want to delete all items? Actually, I do. Okay, so what do I need to do to copy this? Oh, there we go. Copy. Okay, so now if I go into my paste, then there is that structure. Okay, so it sounds good. Oh, great. So I'll just hit enter and get rid of it. Or not. Okay, so now let's run the integral. So then that's easy. I am in cast mode. I'm checking my, I'm in degree mode. I might not want to be in degree mode. Well, for this problem, I guess there's no trig, but keep your eye on that. Okay, so here we go with math. I'll be right back. I got to reboot this. All right, so we're building the integral now, and it is inside of calculus, and we want to integrate, and I want to integrate from 0 to 300, and then I'm going to put my function there. So now it's just a matter of going into paste and choosing that function. And then with respect to x, and 270. Okay, so 270 people get in line over that 300-second interval. So let's answer that question. And then let's put that number over here, and we will compute that. Okay, so I'm going to make quick work of that. And that is 80 people. Okay, so there are always people in line. How many people are in line at time 300? Yeah, 80 people. Okay, got it. Let me move on then to part C. Okay, for time greater than 300, what is the first time t that there are no people in line for the escalator? Okay, so we know that at time 300, then there are 80 people in line. And we know that after time 300, no more people get in line. Okay, so at time 300, there are 80 people in line. And then people are leaving the line at a rate of 0.7 t. So what we want to know is, when is this equal to 0? So then that's just a quick little algebra problem. All right, so I'm not going to do that problem. I'll save that for you to do. That's sort of too easy for a calculus class. But that is 114.28. Okay, so what is the first time t that there are no people in line for the escalator? Now, be careful here. This is the number of seconds that it takes for these 80 people to leave the line. All right, meanwhile, 300 seconds have already passed. 300 seconds passed to get to the point where there were 80 people in line. So then the total amount of time to clear out the escalator line is 414.28 seconds. Okay, so then let's go to part D. And part D, I might recommend pausing this and thinking through these yourselves before I get rolling on them. But of course, for the sake of this video, I'm just going to get rolling on them. But I would recommend pausing it and thinking on your own, and then seeing if your thoughts turn out to match up with mine. Okay, so this one is for the interval 0 to 300. So in terms of that piecewise defined function up above, I'm only worried about the top part of it. At what time t is the number of people in line a minimum? Okay, so now we're doing some optimization. So this seems like differential calculus. To the nearest whole number, find the number of people in line at this time, justify your answer. Okay, so in order for me to minimize the number of people in line, I need a people in line function. So I'm going to call this P at t. So P at t represents the number of people in line at time t. And the number of people in line at time t is the number of people who have entered the line over a certain t many seconds. Then the 20 people that were already in line minus the people who have left the line. Okay, so this first part is the hardest part, but the number of people who have joined the line after t many seconds is this integral, where I have to put an open-ended variable up there, t. Because we went from 0 to 300, and that found the number of people who joined the line or entered the line after 300 seconds. But we don't know how many seconds, so we're sort of just going after an arbitrary amount of seconds. So then that is our rate of change function. I'm not going to rewrite it, dt. And we're talking about just the top half of that piecewise function as a result of that's the interval we're looking at. Okay, so then that's the number of people who have joined the line after t seconds. Then we have the 20 people in there that started in line. And then we subtract from that the number of people who have left the line after t many seconds. Okay, so then that is our people calculator, our people in line calculator. And what we're trying to do is we're trying to minimize that. All right? At what time t is the number of people in line a minimum? So we want to minimize this function. And of course, the way you minimize it is you have to remember differential calculus here, but we take the derivative and then set it equal to 0 to find peaks and valleys. And then that will represent some times where the line either has a critical number of people in line. Maybe it's the least amount of people, or maybe it's the greatest amount of people. And then we could test those by just dropping them in to this very people calculator and see which one is less than the others. Yeah. And then I guess there is also the argument of checking the extremes. Like maybe the least number of people in line ever is the 20 people who start there, and we'll know that when we drop in our values. Okay, but what we need to do is we need to find p prime. So then, to find p prime, we need to differentiate each of these pieces. So we're going to differentiate this one. And we're going to differentiate this one. That'll be 0. And we're going to differentiate this one. That's an easy one. So the only one that's really problematic is this first one. But it's not problematic at all. It's a conceptual piece of math where we're looking at a function who's been integrated but then right round differentiated. So then, of course, we just get the original integrand back. So we're looking at r at t plus 0 and then minus 0.7. And we want to set that equal to 0. All right, so now I'm going to go and use the calculator to do that, because that's a super complicated function to work with. Let me grab my calculator, and we will solve that function. Okay, so there's a couple ways to solve it. I suppose you could send this over and graph the function, see where they intersect. Imagine that we could put it into like the solve feature and see what happens. So there's a variety of ways. We could just graph this one and look and see when it is at height 0. Of course, you're going to need to think about an appropriate window. Time goes from 0 to 300, so that would be the inputs, and the outputs you'd only be interested in the x-axis. So you could go like -1 to 1. All right, we got a variety of ways to do it, and maybe I'll show you a couple. Okay, so my preferred method of solving this is going to be to avoid the graph, just because of the zooming in and out, which is frankly a little hard on my computer version of this calculator. And there is a solve feature, so let's just go into solve, and I'm going to solve this exact equation. So here it again comes in handy that we haven't, or that we copied. So there is the function, it's on my list, and then I'm going to minus 0.7 and set that equal to 0, and then just solve it. And okay, so then we've got 33.01 and 166.57. So what were those numbers? 33.01. Like time 1 and time 2. And time 2 is 166.57. Okay, so then what the heck are we doing? So we have this people in line calculator, and then we are trying to minimize it. So we've taken its derivative and set it equal to 0. So these are the two critical points, the critical times. They're not necessarily corresponding to when the fewest number of people are in line. It might represent when the most people are in line. Okay, so then I'm going to sort of test all these. One thing that I know is that at time 0, the number of people in line is 20. That may very well be the answer. I don't know. And then at time 33.01, I need to calculate that, which means I need to go back up to this function and put in 33.01. Okay, so, back to the calculator. So that is the integral. And we're going to go from 0 to 33.01. And that our function is inside of my paste. So there it is. And then that's going to be dx. And what am I going to do that? Oh, I'm also going to add 20. And I'm going to subtract from that 0.7 times 33.01. Just double checking I got everything correct. Heck of convenient having that in the paste on the clipboard. Okay, so then, ooh, interesting. What's up with that? Okay, I don't really know why they write a program where you can't add something onto the integral, but it looks like the problem was just like this extra part. You can see what I've done. Well, I took a little pause there. I just copied this and deleted a bunch of it, but then there's the integral. So then to this number, copy that, and then I'm gonna add my 20 and subtract my 0.7 times 33.01. Checking that real quick. Oh, so 3.8 people in line. I'm thinking that's going to be the low one. But let's go ahead and quickly test. Whoops. 166.57 seconds. And see what's up with that. Okay, so let's see. The good way to make quick work of this is to take this whole integral and copy it, and then just change that upper limit, which is now 166.57. I've got that answer. I'm going to add 20 to that and subtract the 0.7 times 166.57. Okay, so, and then that number is 158. Okay, so all of this work is probably good to have because they did say to justify our answer, so then we're justifying this. Okay, so then let's see, what's the question? To the nearest whole number, find the number of people in line. To the nearest whole number, 4 people. And I suppose at what time t is the people in line the minimum, and then that happens at 33.01 seconds. All right, I suppose we should be testing what happens at 300, number of people in line at 300. Didn't we already have that one? People in line at 300, that was 80 people. Was that 80 people who have joined the line, or was that having dealt, oh yeah, that was having dealt with the people leaving the line as well. Okay, so then there's my justification and my answers. This then is the assignment, part 1. So it is another question from the AP Calculus test, calculator section. And I think you can use some of the tricks that I showed you. You are certainly welcome to pop into a meet and talk to me about any part of this problem. And as I mentioned, you can also meet with one another in your own Google Meet and use the live board. Okay, thanks everybody.